Okay, everybody, welcome to heat transfer. Here we have a problem. Go ahead and pause the video and read this problem and maybe even draw the diagram so you understand it. I'm not going to stop for it, really. But basically, we're just going to go through this real quick and figure out all the properties and figure out what the heat transfer coefficient is for a sphere of pure copper. So, setting this all up, mainly it's just finding equations and then plugging and chugging. What I'm going to do is I'm going to try to use the lump capacitance for this because we're trying to find the heat transfer by figuring out how much energy that sphere can store. We've got theta over t is equal to theta of t is equal to theta I, exponential of negative t over rt ct. This is the equation for the lump capacitance method, where r of t is equal to 1 over h a of s, ct is equal to rho v c t, which is specific heat, and then theta is equal to t minus t infinity. Theta I is equal to ti minus t infinity, which is t initial. And then the area of the sphere is equal to pi d squared. The volume of the square is equal to pi d cubed over 6. Okay, so going ahead and doing this, what we're going to end up with is taking this equation down and actually subbing in the thetas for temperatures, because we have to figure out at a certain time we can use the temperature at the time 69 seconds, which was given at the beginning of the problem, in order to figure out what the heat transfer coefficient is. So we're going to try to find out what tau is first. So, if we have t minus t infinity all over ti minus t infinity is equal to exponential of negative t all over tau t. Okay, so this is the lump capacitance method here. We're going to go ahead and use t at 69 seconds. And then we're also going to use t of 55 degrees, which is the temperature at 69 seconds. Maybe I should let you see it. T at 69 seconds, and then t initial, which is 66 degrees. So we're going to go ahead and do 55 minus 27 degrees C, all over t initial, which is 66, minus 27 degrees C, is equal to the exponential of negative t, negative 69 seconds, all over tau t. Okay, now you can solve for tau. And if you go ahead and do this algebra, it's actually pretty easy. You should end up with a tau equal to 208.28 seconds. Okay. And the reason this is so is because tau is equal to RTCT. So if you're wondering where I got this as part of the equation, you can either memorize this equation or memorize that tau is equal to RTCT, or so on and so forth. But actually, you have to remember this relation all the way through, because in order now to get h, well, we see that RT is 1 over h of AS. So if we have tau is equal to RTCT, then that is equal to rho VC, oops, not rho VC, rho CP, all over h A of S. Well, there's our h. We can get area, we can get volume, we have density, and we have the coefficient of specific heat, and we can go ahead and solve this out. Now, I'm not going to find these values, the CP and the rho. You can get those from a table. I'm just going to go ahead and sub them in. So, and I'm actually going to change this just a little bit, because this is actually equal. We have AS and V over here. Those can actually cancel, and you get rho LC, which is the distance for the lump capacitance method, times CP, all over H. And this simplifies our problem a little bit more. And LC is equal to R of the sphere, our sphere, all over 3. So if you solve this out, you end up with equal to 12.7 millimeters over 6, because that's the diameter divided by 2 times 3, which is equal to, what was the value that I got for that? It is equal to 0.002 meters, basically. You can put that into here, and solve it out and solve for h with respect to rho, because you have rho 2, it's this value up here. Or you can go ahead and do this volume. I'm actually going to go ahead and do this volume and area because this will work for any situation that you have, basically. The LC, you have to remember this little side formula. So while this is easier, if you remember this little side equation, this equation will always work for any kind of geometry, where this is dependent on the geometry, because LC is dependent on whether it's a sphere, or it's a plate, or it's a bar, or something. So I'm going to go ahead and use this. So I've got 208.28 seconds, which is my tau, is equal to rho for copper is 8,933 kilograms per meters cubed. Volume is equal to pi times the 12.7 millimeters, which is 0.00127 cubed meters cubed, because for volume you have to cube the distance, divided by 6 for volume, times 389 joules per kilogram Kelvin. Okay, so that's our top part of this equation. And then it's divided by HAS, and the H is what we're trying to find. So we've got H times pi times, again, the millimeters converted to meters. Sorry. Pi times 0.0127 squared, meters squared, just carrying that square root through, times 208 seconds. Oops, no, not 208 seconds yet. Sorry, jumped ahead of myself a little bit. Okay. Now, you want to solve for h. So you multiply h over here and you bring 208 back down here. So I'm going to go ahead and cancel this, bring it up here, h equals, cancel this, and bring it back down here, 208.28, just to finish off this equation. Then you just crank out all these numbers, and you should end up with h equal to 35.3 watts per meter squared Kelvin. And that's your answer. Now, there's one thing that we didn't do with this problem because it was basically just assumed or told us. It was that we could use a lumped capacitance method. Normally, you can't just jump into LCM right away. You have to prove that it's possible by using the bio number. And for LCM to be valid, the bio number has to be much greater than 1, or as a general rule, less than 0.1. So bio number is equal to H LC all over K. Now here's this LC. If we had solved for this earlier, then we could have jumped to this equation. And this is where you need LC. You have to use LC in order to prove the bio number. So this is something you'll almost never be able to use unless you're told specifically that you can use lumped capacitance method, because that means you can ignore this whole little section. This is just to prove that lumped capacitance method is valid. So if we solve this out, we end up with 35.3 watts per meter squared Kelvin. Oh, quick comment here. I'm using this H from right here. We just used lumped capacitance method to solve for H, but in order to make sure that H is true and that lumped capacitance method is valid, we have to take H, put it into the bio number equation here. So you can't do this calculation before you solve for H, but we assume that lumped capacitance is correct, but we have to prove that this lumped capacitance can be used by putting this H back into the bio number. So, sorry for that confusion. I jumped ahead of myself a little bit. 0.0127, which is, oops, sorry, LC. We solved LC up here. 0.002 meters divided by 398 watts per meter Kelvin. If you solve that out, you end up with BI equal to 1.88 times 10 to the negative fourth, which is much less than 1. So LCM is okay, and this value is okay. If LCM wasn't okay, then H isn't the right H, and you have to use some other method.